Hello everyone, welcome to He Classroom about Introduction of Physics. Today we are going to talk about force and motion. Up to now we've been talking about motion, especially acceleration, which we know is just a change in velocity. But that naturally leads to a deep questions: what actually causes that change? What makes something accelerate? The answer is a force. A force is simply a push or pull acting on an object, and it's what changes the object's motions. Let's think about a couple of everyday examples. When a car moves forward, it's not just the engine doing the job. The engine provides power, but it's actually the friction between the tires and the road that pushes the car forward. The friction force acts on the direction of motion and causes the car to accelerate. On the other hand, if a car crashed into something, for example a telephone pole, the pole will apply a force onto the car and bring it into a stop. Now I should mention that many students find this part of the course a bit more challenging. There are a couple of reasons for that. First, we now have to deal with vectors when setting up equations. We cannot just work with simple scalars anymore. Direction matters a lot. Second, you start to see a wide variety of physical setups. Objects might be moving along floors or ceilings, inside elevators going up or down, connected by ropes, or even tied together in a more complicated way. And first, all these different situations can feel overwhelming, but here's the key point. For all these kind of varieties, most of the problem can be solved using a very simple central idea, that is the Newton law. So what we are going to do in this chapter is focus on how to apply the Newton law to all these different situations. Once you get comfortable with that, all the problems become more manageable. Now, the relationship between force and accelerations was first clearly understood by Newton, who lived in the 17th century. What he developed is what we now call Newton mechanics, the study of how a force affects motions. But it's important to realize that Newton mechanics doesn't apply to every situation. It works extremely well for everyday macroscopic objects, things we can see, and for speeds that are relatively low compared to the speed of light. However, when the objects move at a very high speeds, close to the speed of light, Newton's laws are no longer accurate. In those cases, we need to use Einstein's theory of special realities, which correctly describe motions at any speed, including those extreme cases. On the other end of the scale, if we look at very tiny objects, like electrons inside an atom, Newton mechanics also breaks down. There we have to use quantum mechanics to describe these behaviors. So from a modern perspective, we can think of Newton mechanics as a kind of approximation. It's a special case of these more general theories, but it works very well for most everyday situations. That's why we still use it so much. Before we start applying Newton's law, let's take a moment to talk about a couple of basic features of forces. First, the unit of force. In the SI system, the unit is called Newton. 1 Newton is defined as the force required to accelerate a 1 kilogram mass at a rate of 1 meter per second squared in the direction of the applied force. So in terms of units, 1 Newton is equal to 1 kilogram times meter per second squared, like they here. Now, if you are working in the British system, the unit of force is different. Instead of newtons, people typically use pounds. Second, force is a vector quantity. That means it has both magnitude and directions. So when two or more forces act on the same object, we cannot just add the numbers. We have to add them as vectors to find the net force. Let's look at how that works. Suppose we have two forces F1 and F2. To add them, we use what's called the head-to-tails method. We take one vector and place the tails of the second vectors and the head of the first. When we do that, the vectors that goes from the tail of the first to the head of the second, then we have the net force, which we call F net. So visually, we are combining the two forces into a single equivalent force that has the same overall effect on the object. Okay, now let's talk about Newton's first law. It says that if the net force acting on an object is zero, then its velocity does not change. In other words, an object at rest will stay at rest unless a net force acts on it. It's important to note that there can be multiple forces acting on an object, but as long as those forces balance out, so that net force is zero, there's no acceleration and the motion doesn't change. Now, what about objects that are already moving? Let's think about a simple examples. A park sliding on a surface. A park across a wooden floor. You notice that it slows down and eventually stops. That's because of friction acting on it. If you actually want the park to keep moving at a constant velocity across the floor, you will need to keep pushing or pulling it continuously to balance on that friction force. Now compare that to a park sliding on ice. Like in skating rink, it travels much further before slowing down. The surface is more slippery, so the friction is much smaller. You can even imagine that an ideal situation, a perfectly frictionless surface. In that case, once the park starts to moving, it would never slow down at all. It would just keep moving at a constant speed. So this gives us an important idea. If we observe that an object is moving across a surface with constant velocity, that tells us the net force acting on it must be zero. And from that, we come back to Newton's first law. If no net force acts on an object, its velocity cannot change, which means the body cannot accelerate. As Newton's first law mentioned, if no net force acts on a body, the body's velocity cannot change. That is, the body cannot accelerate. Then what if the net force is not zero? When we apply a force on a body, then it gives the body an acceleration rate, bring a body from stop to move or from move to stop. As a daily observation, the acceleration rate is proportional to the force. Strong push results a faster speed up, while a weak push will have a slower speed up. Meanwhile, acceleration is inversely proportional to mass. So if you apply the same force, a heavier object will speed up more slowly, while a lighter one will speed up more quickly. Based on the daily observation, then it comes to Newton's second law. the net force is equal to the product of the body's mass and its acceleration. In equation form, it is F equal to ma. Like other vector equations, next one can be separated into three component equations, one for each axis of our XYZ coordination system. Each of these equations relates the net force components along our axis to the acceleration along that same axis. For example, the first equation tells us that the sum of all the force components along the x-axis causes the x components ax of the body's acceleration, but causes no acceleration in the y and z directions. Turned around, the acceleration components ax is caused only by the sum of the force components along the x-axis. It is completely unrelated to force components along other axes. Okay, now let's see how Newton's law is applied to solve our force problem. Here we have a cube on a slope. First, we need to identify the body. Find all the forces acting on that body. Here we have a dragging force for F1, friction force applied by the slope, F2. It is opposite to F1. Then the body has its own gravities, we term it as F3, and then a support force from the slope termed as F4. Once we find all the forces on that body, go to the step 2, separate axes. As we mentioned above, the net force component along our axis causes the acceleration component of the body along the same axis. Here, we first define the axis as along the slope as x-axis and the y-axis is normal to the slope surface. Then we can see that F1 and F2 are both along the x-axis. F4 is along the y-axis. But the body gravities F3 is not either axis. To solve the problem, we need to separate it into the axis. It can be separated into F3x and F3y, just as here. So once we have all the forces aligned on the axis, we move to the step 3, finding the forces in equilibrium. Newton's law tells us if the net force on a body is 0, the body's acceleration should be equal to 0. If the body is at rest, it stays at rest. If it is moving, it continues to move at a constant velocity. In such cases, any forces on the body will balance one another, and both the forces and the body are said to be in equilibrium. Commonly, the forces are also said to cancel one another. Here, if this body is in equilibrium, then we will have on the x-axis, F net x should be equal to F3x plus F2 plus F1 should be equal to 0. On the y-axis, F net y should be equal to F3y plus F4 should be equal to 0. To solve problems using Newton's second law, we usually start by drawing a free body diagram. In this diagram, we focused on just one object, the one we are analyzing, and represent it as a simple dot. Then we draw all the forces acting on it as arrows, with their tails starting from the object. We also choose our coordination system, usually with separate axes, to help us keep track of directions. If the object is accelerating, we can show that with the arrow as well. An important point, we only include external forces acting on the object. Internal forces don't affect the motion of the object as a whole, so we leave them out. Okay, that's all for today. See you next